The LI for this lesson is to be able to understand and use Newton's third law and solve problems involving connected particles. So what we can do is, if a system involves motion of more than one particle, we can consider them separately. Nice and simple to just think about each particle on its own. However, if they're moving in the same straight line, then we can also treat the whole system as a single particle. And that's basically saying that if the particles are moving together in one straight line, the same direction, then we can just treat them as one object. So treat the whole thing together as one. And it says, watch out here, they must remain in contact or be connected by an extensible rod or string to be considered as a single particle. So that's just saying that they must always maintain that same distance apart. They can't start moving relative to each other. They must maintain the same distance apart. So let's have a look then at question 11. Two particles, P and Q, of masses 5 kilograms and 3 kilograms, are connected by a light extensible string. P is pulled by a horizontal force of 40 newtons along a rough horizontal plane. P experiences a frictional force of 10 newtons and Q experiences a frictional force of 6 newtons. So the first thing I'm going to do is make a quick sketch. So this is the plane that they are being pulled along. And so I've got particle P. This is particle P. And particle P is 5 kilograms. And we've got particle Q, which is connected to particle P by a light inextensible string. And Q is 3 kilograms. And then I'm going to start putting some of these forces on that they've told us about. So particle P is pulled by a horizontal force of 40 newtons. So I'm going to go back to the right, 40 newtons horizontally. In this string, we know there is going to be a tension, so I'm going to label that as T. And we talked earlier on about how the tension will be the same throughout the string, and I know that because it is an inextensible light string. Then it's got some other force going on, so we are told that there's a frictional force of 10 newtons on P, and that's going to act opposite to the direction of motion. So we've got 10 newtons, putting there, that's a bit small. Then Q has a frictional force of 6 newtons, so again, that's going to act opposite to the direction of motion, 6 newtons. And we can always put on the weight, so we know this is going to have 5g, remember I've got 5 kilograms times by the acceleration due to gravity. Here, this one is going to be 3g. And then I'm going to have some reaction forces, so I'm just going to call this R1, and I'm going to call this R2. We can actually see that those reactions will be equal to the weight, but it doesn't really matter. I'm just going to put R1 and R2 on. And I know that this system is, the first question is find the acceleration of the particles. Well, if P is being pulled along to the right, the particles will be accelerating towards the right. So I know that the acceleration will be in that direction. So for the first question, I'm going to this time decide to use the whole thing and look at the whole system. And I can do that because remember it said that the particles need to remain in contact or be connected by an extensible rod or string. Well, they're connected by this inextensible string. So I can look at the whole system. So I'm going to put a bit of a box around this whole system. This is what I'm going to be focusing on first. I'm looking at the whole system. So for A, I'm going to say whole system. And we looked in the last chapter about if I want to find the acceleration, I can use that the resultant force is equal to the mass times the acceleration. Well, that means I know the total mass of the system is going to be 3k plus 5k, so the total mass is going to be 8 kilograms. The acceleration is what I want to find out. And first I can just resolve forces, work out the resultant force. So let's move to the right. And I'm looking at the whole system, remember. So here, where I've got the tensions, I really need to include them because I'm looking at the whole system. Those two tensions just cancel each other out, happening within the system. So in terms of forces on the whole system, I've got 40 newtons, which is going out here to the right. And then forces that are to the left, well, I've got this 10 newtons here, so I'm going to take away 10. And I've also got 6 newtons here, so I'm going to take away 6. And I know that the resultant force is equal to the mass, which is 8, times the acceleration, which is what I'm going to work out. So you can just resolve that. So we get this is 24 is equal to 8 acceleration. So the acceleration is equal to 3 meters per second squared. And that is my answer there, finding the acceleration. Then part B, let's see, where should I do this? I'm going to try and squeeze part B up here for now. So part B said find tension in the string. Now, I can't look at the whole system anymore because we just said that in the whole system, these tensions don't really come to play because they cancel each other out, so I won't be able to resolve. So this time I'm going to look at just one of the particles. I'm just going to look at particle P, start drawing a bit of a box around here. All I care about this time is particle P. I want to find the tension in the string. Well, I know that the resultant force must equal the mass times the acceleration. This time the mass is 5 kilograms. The acceleration we just worked out is going to be 3 meters per second squared. So I know the resultant force must equal to 5 times 3, which is 15 newtons. So let's resolve. Well, if I resolve particle P to the right, I've got 50 newtons going off to the right. I've got 10 newtons going off to the left, so I need to take away 10. And I've also got the tension going off to the left, so I need to take away T. And that equals 15, because 15 is my resultant force. And then if I resolve that, I get that 30 minus T equals 15. And therefore, I'm going to get that T is equal to 15 newtons. Now, I just did that by looking at particle P. If you wanted to, you could look at particle Q, do the exact same thing, and you would still get that T is equal to 15 newtons. Both those tensions will be the same. So if you've got some extra time, try that out, work out what T is there, and hopefully you'll get an answer of 15 newtons. The final part, part C, is asking about our modelling assumptions. So it says, explain how the modelling assumptions the string is light and inextensible has been used. Well, these are what we talked about back in the first chapter of mechanics. Sorry, let me just squeeze that in here. So if a string is inextensible, this means that the acceleration of the masses is the same. And that's because the string isn't stretching, it's staying exactly the same distance apart. So if P is moving at a certain acceleration, Q will also be moving at acceleration because the string is staying the same length, so they're both moving with the same acceleration. Then, if the string is light, well, as soon as somebody says something is light, we know that we're going to ignore the mass. So the mass of the string is negligible. I always spell this one wrong. Which just means that it's going to be so small that we don't really need to include it in our calculations. So it's light, and also the tension is the same throughout the string. And so that's what we mean when we've said light and inextensible. Let's move on to the next page. And on this next page, we are now looking at Newton's third law. And Newton's third law says that for every action, there is an equal opposite reaction. Nice easy one to remember that one. And really what that's saying is that if we've got two bodies, A and B, in contact, and body A exerts force on body B, then body B will exert the exact same force on body A. It'll be in the opposite direction, but it'll be the same size. And we've kind of seen that already. We talked about things like a book on a surface. You've got the weight of the book pressing down onto the surface, so let's say that's 5 kilogram book, pretty heavy book there. Then we also talk about reaction. So the reaction from the surface back to the book is it's the same magnitude but an opposite direction. And that is just Newton's third law. Every action has an equal and opposite reaction. I'm going to use that for example 12 now. So example 12 is about a light scale pan attached to a vertical light inextensible string, so we've got those assumptions in there again, and it carries two masses, A and B. The mass of A is 400 grams and the mass of B is 600 grams. A rests on top of B as shown by diagram. And the pan is raised vertically, so somebody's lifting it up using the string, so we know there's going to be tension here in that string, with an acceleration of 0.5 meters per second squared. So it's accelerating upwards at 0.5 meters per second squared. And the first thing is to find the tension in the string. And to do this one, I am going to consider the whole system. So I'm going to look at the whole system. And I'm allowed to do that because these two masses are always staying in contact. They're always staying in contact with the steel pan. Nothing is moving relative to each other, so it's all fine. And so find the tension in the string. Well, I know that the resultant force is equal to the mass times the acceleration. And we're talking upwards here, so I know the acceleration upwards is 0.5 meters per second squared. I know that the mass, well, I know that this scale pan, is light. That's what it told me, so we don't need to include that mass. The string is light, so we don't care about the mass of that either. So the only masses I'm actually concerned about are A and B, and together they make 1 kilogram, so the mass is 1 kilogram. So I know that the resultant force is equal to 1 times 0.5, which is 0.5 newtons. So the resultant force upwards is 0.5 newtons. So let's resolve vertically on the whole system. And I'm just going to add in some of the forces that we've got going on here. So from B, we're going to have a force downwards that is going to be 0.6 G. And from A, we're also going to have a force downwards, which is 0.4 G. If I'm resolving for that whole system, I'm going to have T is the force upwards, take away 0.6 G, take away 0.4 G, and that is equal to the mass times the acceleration, 0.5. And so I'm going to have T minus G, 0.4 and 0.6, that makes 1, is equal to 0.5. And therefore the tension is equal to 0.5 plus G, which is going to be 10.3 newtons. Remember, just as a side note, G is equal to 9.8 meters a second squared. And so this is two significant figures. If we would just get that T is equal to 10 newtons. So that's my answer there for finding the tension in the string. Now the next one says find the force exerted on mass B by mass A. So if I'm looking here at mass B or A, I'm going to focus on mass A. So if I draw out mass A, well, I know that the weight downwards of mass A is 0.4 G. Oh, sorry, let me just move that in here. I know then I'm looking for this force off B, so the reaction force coming off B. I also know that the mass is accelerating upwards with 0.5 meters per second squared as the acceleration. So focusing on A only, if I resolve this system and I find out what R is, that is the force on A by B. So let's have a look. I'm resolving upwards. Upwards I've got R, so I need to take away 0.4 G, and I'll get my answer is equal to the mass times the acceleration. Well, the mass here is 0.4 kilograms, so 0.4 multiplied by 0.5, which is the acceleration. And so if I resolve all that, I get that R is equal to 4.12 newtons. And so just to make that super clear, I'm going to say the force exerted on B by A is 4.12 newtons. So what we really found here is the force exerted by B on A. They asked for the force exerted on B by A. So what I've got here is the force exerted on A by B, but we know because of Newton's third law it's going to be the same. And then finally for part C, it's finding the mass of the scale pan. Find force exerted, by B on the scale pan. So let's draw a bit of a diagram of what we're talking about here. So here is my pan. I'm only going to focus on the pan now. I'm going to ignore the particles on the inside. I'm just looking at the force that are on the pan. So I know that there's a tension upwards from that string. Then I also know that I'm going to call it S, this force that B is exerting on the pan. I don't know what it is, but I'm just going to call it S for now. And like all the other particles, the pan is accelerating upwards with an acceleration of 0.5 meters per second squared. So focusing on the scale pan only, I'll do exactly the same as I've done before. I'm resolving. So I've got the T resolving upwards, T going upwards, take away S going downwards is equal to the mass times the acceleration. However, the mass of the scale pan, we're just assuming is 0 because it's a light scale pan. So it's just going to be 0. And therefore, T is equal to S, which means that S is equal to what we found for T before, 10.3 newtons. 10.3 newtons, which means that the force exerted by B on the pan is 10.3 newtons. So for that third one, for the part A, we looked at the whole system. For part B, we looked at just one of those masses, and for part C, we looked at just the scale pan. So that's demonstrating how we can look at either the whole system or the different particles involved to solve some of those problems. Okay, you should be able to have a good go now at exercise 10E. That includes using either the whole system or looking at particles, and Newton's third law about every action having an equal and opposite reaction.